So yeah, hi everyone. My name is Fedor. Today, surprisingly, I represent a company called Arrival. We sort of build real vehicles, and I'm gonna talk today about some experiments we've done with this amazing team that you can see the names in our R&D lab about simulation to reality transfer for peg hole insertion with in-hand camera. So it's somehow related to the previous talk, like really amazing stuff. I really like that. So we have some background already covered. I will actually start from showing the results. So here on the video, you can see a neural network controller trained in simulation solely on grayscale images, successfully performing insertion on the real robot. So on the left video is a little bit speeded up. On the bottom, you can see actual input to the neural network. And on the right, you can see real world time performance. So as we are talking on behalf of industry here, a real need for flexible manufacturing brought us here. And for robotic assembly that we're talking about, flexibility comes mostly with the cost of uncertainty, for example, for parts placement. Also, like this used to be solved by doing external pose estimation, for example, then doing planning, then executing the trajectory. But this leads to summing up all the errors of all the methods. And also if we have occlusions, then we have problems with external sensors. And we are asking ourselves, like, how much of this uncertainty can we solve with vision only? And we want to implement a vision, like closed vision control loop. And we want it ideally to be trained. And why training? Because we actually don't want to do programming for every new scenario that we get in the assembly. We want to have a general framework that will allow us to train a controller. And here is our experimental setup. So we chose peg and hole as it is well studied in literature. So there are a lot of references. And also it is a very good proxy for different tasks in real assembly, for example, screwing or insertion. But most of our references when using vision for this task choose to use external cameras. But we found it much more suitable, much more interesting, you can say, for direct vision feedback to have camera placed on the moving end effector, as the image in this case has much stronger relation to actual movement. So it's actually active vision, and also an advantage of having better resolution as we approach the target, let's say. And effectively, we can say that in this case, we want to learn a visual serving controller. And we choose, as in the previous work, we choose to use reinforcement learning framework for that. So here's how the training looks like. So we can see a scene and simulation on the final stage of training where it actually has almost 100% success rate. And some of you familiar with the reinforcement learning framework know that the reward design is sometimes crucial for successful learning. And we started from reward consisting of 4 parts based on the distance, smooth reward, and sparse reward for achieving success state, and also negative for collision and spending time. But we found out that actually most of this is redundant, so you can successfully train a policy with only distance-based reward. What we learn is that like during the experiments, we learned that for vision-based controller, proper reception input is not actually critical, so it works as well without. And as the same is for depth, but maybe it was particular because of the sensor we used, because we used active stereo camera. And we found out that using such noisy depth sensor can actually reduce performance when doing Sim2Real transfer because of the very specific, let me start the video. So you can see the very specific pattern of the noise, which is hardly can be modeled in the simulation, and it seems like there is no need for that. So if we just remove depth from observation space, we get the same precision and much better Sim2Real transferability. And although there is still some sensitivity to external factors such as illumination and also sensitivity to hand-eye calibration, on the positive side, we see that the policy is able to generalize to bigger pegs. So on the bottom video, you can see that the policy performs insertion with the significantly bigger peg, but this is still the same neural network. So we hope that it actually learns some general features required for the task. And also, interestingly, if you draw attention to the trajectory that is chosen on the bottom video, you can see that it sort of chooses to move in such a way that it sees most of the whole till the very end of the trajectory and only starts final adjustment when like reached maximal resolution of the image, like in the maximal proximity to the target. And for the future work, we assume to like conquer some problems we encountered in those experiments, and most interestingly, maybe move towards general controllers. So rather than learning a particular scenario, learn a general skill of inserting like a peg into a hole, which is we find most interesting.